In question 2a, we're told a fluorescent tube is filled with mercury vapour at low pressure, and in order to emit electromagnetic radiation, the mercury atoms must be excited. In part 1, we're asked what is meant by an excited atom. Well, an atom is excited when it has an electron in a higher energy level than the ground state. In part 2, we need to describe the process by which mercury atoms become excited. Well, in a fluorescent tube, electrons move through the tube, they collide with the mercury atoms and raise the electrons to higher energy levels. In part 3, we're asked to state the purpose of the coating on the inside of the glass in a fluorescent tube. Well, the excited mercury atoms emit ultraviolet photons. These then are absorbed by the coating, and the coating then re-emits photons in the visible part of the spectrum. In B, we're shown the lowest energy levels of a mercury atom, and in part 1 we need to calculate the frequency of an emitted photon going from n equals 4 to n equals 3. Well, the energy of the photon will be the initial energy minus the final energy of the electron as it drops from the n equals 4 to n equals 3 states. Notice here we have minus a minus term. This gives an energy of 0.33 times 10 to the minus 18 joules. Then we can use E equals hf, where h is the Planck constant and f the frequency. Rearranging, we get the frequency is the energy of the photon divided by the Planck constant. Putting in the values given, the Planck constant is on the formula sheet, gives a frequency of 5.0 times 10 to the 14 Hertz. In part 2, we're asked to add an arrow to the figure to show a transition emitting a photon with a longer wavelength than that of the n equals 4 to n equals 3 transition. Well, the transition must be of a lower energy to give a longer wavelength, and this will be from n equals 3 to n equals 2. Just to check, this gives an energy of the n equals 3 level minus the n equals 2 level, which is 0.29 times 10 to the minus 18 joules, less than we found here.